Okay, and now in question 4, we've got another manufacturing plant in question. And this one makes skis, snow skis, downhill skis, and slalom skis. And we're told that the downhill ski requires 3 labor hours for fabricating and 2 labor hours for finishing. The slalom ski requires 5 labor hours for fabricating and 3 labor hours for finishing. That just means it takes them 5 labor hours to make a slalom ski unfinished, and then the finishing department takes this amount of time. And we're asked to summarize that information in a table. Now, remember that in this table, you'll need a row for each process. There's only 2 processes, so you need a row for each process. And you need a column for each type of product, plus one last column for the total labor hours that are available. So that you got, however many guys or women you got working. This is the maximum number of hours that your manufacturing team can put in. And so 3 hours spent on the downhill ski and 5 hours spent on the slalom ski are expressed as this inequality here, because we did let x equal the number of downhill skis, y equal the number of slalom skis. This is very similar to the corn and soybean situation, this corn and soybean problem from number 3. And so 3 hours for each downhill ski, 5 hours for each slalom ski, and the one equation is going to represent one process, fabricating, the manufacturing, before finishing. And then the other inequality represents the other process. So we have 2 hours for each downhill ski, so that's why it's 2x, and 3 hours for each slalom ski, so that's why it's 3y. And together those add up to no more than 86. So there's our our system of linear inequalities that describes the feasible conditions at this plant. Now, I know that the practice that I gave you had the first part of the question, but it did not have the second. I want you to go ahead and complete this part. I will add this part to the question on the exam, so make sure that you are prepared for that. Okay, question 5 asks us to graph the solution region of this system of linear inequalities. And I highlighted the blue one because y is not, we don't have a single y here. We're going to have to do something extra to put it in slope-intercept form, if that's what we want to do. You don't have to, though. You could use the intercept method to graph any of these. But in any case, that's what I've done. Is I've put it in slope-intercept form, and maybe it's a little easier to graph that way. Now, the first inequality, though, I subtract 2x from both sides. That gives me y minus 2x equal plus 10. Since the y-intercept is not shown on this graph, you might want to use the intercept method to plot this one. You would want to find the x-intercept by, by substituting a 0 for y and dividing both sides by 2 to find that x is equal to 5. So 0 here, and this divided by 2, and this divided by 2 would give you x is equal to 5, and so that's your x-intercept. And then for the slope is going to be -1/2. And so that means that you would go down 1 and over 2. And so this is a little bit tricky because you would need to count backwards. You'd need to go backwards, left 1, up 1, to find the next point of a with a negative slope. In any case, this is the line right here that represents the first equation. 2x plus y is less than or equal to 10. And then for the next equation, the one that I mentioned earlier, the blue one, you would find that your y-intercept is 5. So you'd plot a point here, and then because the slope is -1/2, you'd go down 1 and over 2, and so there's another point right there, and so those 2 points would describe your line. And then the last one, for the last one, you can again use the y-intercept, because when you subtract x from both sides, the y-intercept is shown to be 6. And the slope is -1, so you'd go down 1, over 1, down 1, over 1, down 1, over 1, as many times as you needed to find a point that's convenient for you to draw that line. Now each of these is less than or equal to, so we're going to shade below the intersection of all of these three. And we will shade to the right of the x-axis, of the y-axis, because x is greater than or equal to 0. And we would shade above the x-axis because y is greater than or equal to 0. So that's why we have this sort of diamond-shaped shaded area here. All of these inequalities include equality, so they are solid lines. And there's our solution set, and this is from section 5.2 if you want to go back and revisit that. Alright, now in question 6 we're going to maximize this equation on this system. Well, what is z? Z is some value that we get for any point on this graph for this equation. And so our maximum value is going to come at one of these corner points. So what you do is you find the coordinates of each of these points. And so for this one, that's x is 4 and y is 9. So the xy pair corresponding to this point is 4 and 9. So you plug 4 in for x here and 9 in for y here. And so that's 16 minus 54. That's -38. Then this point here has an x value of 7 and a y value of 2. So x, y is 7, 2. So you plug 7 in for x here and 2 in for y here. And that's 28 minus 12, or 16, positive 16. Then our last point is x is 8, y is 8. So it's 8, 8. xy equals 8, 8. So we plug 8 in for x here and 8 in for y here. And that's 4 times 8 is 32, 6 times 8 is suddenly I'm drawing a blank. 48, and you subtract 48 from 32, you get negative 16. So this is the point, and I didn't write that answer out here, but this is the point right here that maximizes this equation on this system.